Hello everyone, welcome to part 3, the last part of topic 8, where we should complete the discussion about game theory and how the intelligent agent should react in case of multi-agent environment and like limited resources. We study maybe this famous and well-known example is known as Prisoners dilemma, and let us provide this in maybe some different context. So we say here that we have two students miss the final exam in a particular course because they attended a night party. However, they told the teacher that they had a problem with their car when they were coming together for the exam. So this is the situation, and the teacher agreed to repeat the exam for them. However, on the exam day, he puts every student in a different classroom, so there is no communication between the students. There was only one question. So, are you sure that you missed the exam because of a car or the car problem or some other reason? If you lie, you will be dismissed from the university. It means that if the student didn't say the truth, he or she will be dismissed from the university. How should both students play this game, or how both students should react to this? The payoff matrix of the game is given here, so we can see that this is the by matrix, like payoff matrix of both students. This is for student 2 and this is for student 1. Okay, so you can see here that if both students confess, it means that confess means that both of them tell the truth about the situation, then both of them will get 0 in the course. Okay, so they have to repeat the course or maybe come to the next retake exam. But if the first student tells the truth, confess, and the second student didn't tell the truth, so he or she insists that because of car problem, then the first student who tells the truth, they will get 3 in the course. They will pass the course with a grade 3 as a prize because they said the truth. The other student will be dismissed from the university because he's a liar. He's a bad example, for example. And if the first student didn't tell the truth, but the first one told the truth, so the situation will be like just flipped. So the first student will be dismissed from the from the school, and the second student will get grade 3. Okay, and if both of them didn't tell the truth, okay, both of them, they didn't tell the truth, so the teacher will suppose that he was thinking bad about them, and he will think that both they were saying the truth, and because of that he will give both of them grade 1. So both of them will pass the course with grade 1. Okay, now how could the intelligent agent, or how could you think about to handle this problem? Now we have conflict of interest here. So dismissed here, you may think about it as a negative large number, because when the student dismissed from the school, from the university, for example, it will be a very big like loss. Because of that, we can say that D here is equal to minus mu, and mu is very large number, so it means that very big loss. Okay, now let us study this situation, and then we will see where is Nash equilibrium here. Where is the Nash equilibrium? Where is the equilibrium solution that every student should play? Which is strategy that each student should play? And also we can build, or we can think how the equilibrium point working. Okay, now if both of them confess, then both of them will get 0. Okay, so if both of them didn't confess, then both of them will get grade 1. So grade 1 for both of them is better than grade 0 for both of them. So should they go to this one, that both of them they didn't tell the truth? Actually, if we look to the problem from optimum point of view, of course this should be the optimal solution, that both of them they will get grade 1. However, no one will fully trust the other student, because both of them they are in separate classroom. So if this student think that the other one will not tell the truth, and he or she decided not to tell the truth, so he will say, for example, student 1 decided not to tell the truth, they don't confess. But what happened if the other student play or deviate from this solution? The other student will get more benefit, so they will get, instead of 1, they will get grade 3. But the first student will be dismissed from the school. Then deviating from this solution either up or to the left, it means that the student can do better if by deviating. Then even this solution looks that it is the optimum one, but it is not stable. It is not stable. You cannot rely. You cannot take the risk. So the intelligent agent shouldn't take the risk in this case, because the risk is very high. Okay? And in this case, actually, the 0 tells the truth for both of them. They will be the robust solution, and this will be the Nash equilibrium solution. Okay, now how could we compute the Nash equilibrium? Okay, now if we look to the player 1, so player 1 plays with columns, with rows, as you can see. Then you can just come to the first one, the first option, and the first option in the second row, and check which one is better for the player 1. Which one is better for player 1? Of course, dismiss or 0. Of course, 0 is better. So you put just star above the better solution. Okay? Then you come to the second row, or to the second column. Then for the rows, for the first player, which one is better, 3 or 1? Of course, 3. Then you should put a star over 3. Then this is for player 1. Then we look for player 2. For player 2, we check like column by column. So for the player 2, which one to play? Confess or don't confess? If he or she confess, they will get 0. Don't confess will get dismissed. Of course, 0 is much better. So we put star here. Okay? And then for the second row, which means that the student 1 didn't confess, then for the second player, which one is better, 3 or 1? Of course, the 3 is better. So we put here a star. Okay? Now, you look to the solution which has a star, where both of them, they get star. This solution is called Nash equilibrium solution. This solution is Nash equilibrium in E, and it is a stable solution. This is a stable solution and Nash equilibrium. So even it is not the optimum solution, but this is the solution that everyone should go for it. Okay, is it of course 1 as I said is better than 0. But even in this case, this one is it is more efficient, more optimal, but it is not stable solution. It is not stable because any of them he could do better by deviating from it. And remember that what I mentioned before, and this is very important for Nash equilibrium and in game theory, that the utility function, I will do it in just like, yes. This is very, very important to remember always, that the utility function for player 1, or player 2, or for any player actually, so I put it X, the utility function, that if they play with the Nash equilibrium, and player 2 plays also with Nash equilibrium solution, so both of them, they select the equilibrium solution, then this solution will be always better than or equal to any other solution played by X, given that Y play with the Nash equilibrium solution. Okay, so this solution is always better. This utility, the payoff is always better that if you play with any other solution. So this is the stable and robust solution. It is the equilibrium solution, the Nash equilibrium solution. Even sometimes, as I said, it is not good solution. Sometimes even it is bad, but any player should play it. Otherwise, if they didn't play it, then the other can get benefit of that, and they can do even better. And this is the same for any other players. I mean, we can make it general. So if we assume that we have maybe 3 players, we have X player, Y player, and Z player. So it is always true that YX, if the X play with the equilibrium solution, and Y play with the equilibrium solution, and Z play with the equilibrium solution, okay, this will be always greater than or equal to UX if X play with any other solution than the equilibrium, given that Y play with the equilibrium and Z play with the equilibrium. And actually we can repeat this 3 times. So this is the same for Y. It will be the same, greater than or equal to, if, of course, here equilibrium, Y is equilibrium solution, and Z is the equilibrium solution, greater than or equal to, or the Nash equilibrium solution. This will be U, Y, if X play with the equilibrium solution, but Y play with any other solution, and Z play with the equilibrium solution. And we can repeat it also for Z. So this is general rule. So the equilibrium solution is the solution that every player should play for non-cooperative game. For non-cooperative game, that every player should play it. So if they deviate from it, then the other one can get better, and they can achieve better solution. So if you, for example, player 1, he or she was thinking, okay, let me go, instead of playing 0, I decided to play, for example, 1. If they decide to don't confess to play 1, actually, but the player 2 can get benefit from that by playing don't confess, or by playing confess, and then student 2 will get 3 instead of 1, and the student 1 will be dismissed. So actually, by making such kind of study, we can also be able to understand some of not only for general behaviors, that every mature or intelligent behavior that we can study it. Human behavior sometimes, how people they can react, for example, on the cross traffic light. If many people start to cross the red light, for example, how the others will react for that. So in case of mess situation, when there is shortage in the resources, how people should react or will react based on that. If there is no rules or no strong control in some city, for example, because of light is off or something, there's, for example, blackout in some city, and then we can see the react of some people when there is lose of safety. So also in the level of animals, that we can study the behavior of animals and behavior even for more primitive living shapes, like bacteria, for example. Many of these living creations that we can study them based on this equilibrium concept and how life can like compete for existence and for resources. Okay. Um, of course, this could be done as mathematically, can be put into mathematical form, and then our intelligent agent could be able to react accordingly. Okay, so now we explain this. So another example here. So if I asked you to find the Nash equilibrium here for this solution, so of course it is in this one, of course it is not like zero sum. So a game. So you can see here. So now for player 1, they should start 2 or 1. What do you think? Which one is bigger? 2 is bigger. So let me make star here. Okay, 3 and 4, which one is better? 4 is better. So they will play this one. Okay, now for player 2, that they should play 2 or 1. Of course, 2 is better, so they play 2. And now 3 or 4, 4 is better, then they will play 4. So in this example, actually, we have 2 Nash equilibrium solutions. We have 2 Nash equilibrium solutions. Okay, which one both of them, even if they don't collaborate, of course, every one of them should play this one. Okay, so if player 2 or decided to play strategy 2, okay, then if player 1 decided to play strategy 1, of course player 2 will lose. Okay, but actually player 1 could do better by playing strategy 2 as well. So actually which one is taken if there is no like hidden bad feeling among each other. So every player by default, because now in game theory we assume that the other player is also mature and intelligent, and he or she knows this payoff matrix very well. So then both of them, of course, they will play this one, because both of them, they will get better than 2-2. However, if there is some like hidden feeling against the other player, so I am ready to lose something as far as the other player will lose more, of course, then it can be different in this case. Okay. Yeah. What we have seen so far is 2 players game, but in general, in reality, we can have like in-person games. So the number of players can be n, and also the strategy not necessarily to be discrete, as we have seen. It can be also like continuous strategy as well. So it is quite general. And the strategy parameters can be probability to play, or they can be also money. So the strategy can be money, that how the investment money. It can be power. It can be ideology. Actually, you can also think about ideology as one of the strategies that you play. And this is the same actually for the utility or the payoff. The payoff is not necessarily all to be like money or to be like direct some kind of material losses or gains, but it can be also gains for ideology or for idea or for making some like or transfer some thoughts from place to place and so on. So it is very general way. So in case of in-person games, so by assuming that the strategies are given in this way, so the strategy vector consists of Q1 and the Q1 star means that this is the equilibrium, and each Q here is by itself is a strategy which can be single element or it can be also another vector. So this one can be a matrix or it can be vector. So now we have Q1 star, Q2 star up to Qn star. So in order to have like Nash equilibrium, then for every player that UI, that if all of them they play with the Nash equilibrium, then it will be better than for the ith player if ith player play with any other like strategy than the Nash equilibrium one. Okay, so in that sense, no player can do better by deviating from the Nash point, assuming that no one else deviates. So this is very, very important concept that we should always keep in mind when we talk about decision theory and talking about game theory in general. Okay, so in case of discrete and we have n players, because what we have seen already is only 2 players for this pi matrix payoff. So now if we have, for example, 3 players and we have also discrete case, how could we solve this problem? So it is quite easy also to solve, but in this case we will have more than one matrix. For example, here you can mention about player 1 against player 3, for example, if player 2 plays, for example, the first strategy, and then again player 1 against player 3 if player 2 plays the second strategy, and so on. So for example, if player 2 he has or she has, for example, 4 strategies to play, then we can divide them into 4 different matrices. So we have the player 1 with the player 3 with when the player 2 plays the first strategy, player 1 against player 3 when the player 2 plays the second strategy, player 1 against player 3 when the player 2 plays the third strategy, and so on. And then we can put them in this way, as you can see. So this what you can see here, for example, A11, A111, it means that the payoff of first player when they play the first strategy and the player 2 plays the first strategy and the player 3 plays also the first strategy. So 111 means first strategies for all 3 players. B111 is the payoff of player 2. C111 is the payoff of player 3. And here, for example, if you take this one, it means that A212, it means that the payoff of player 1 if player 1 plays with the second strategy and the player 2 plays first strategy and the player 3 plays second strategy, and so on. So you can simply build them in this way, and actually it is quite easy or straightforward to implement them also in code if you are writing like this game theory in computer or coding them, so it will be multidimensional matrices. Okay. Yes. So what else? Okay, that's all actually about this. What here just we show one way to find the solution in case of in-person games. So here it is sufficient but not necessary conditions for Nash equilibrium point that the derivative is 0 for this is, of course, remember here that the in case of continuous strategies, then we can differentiate them. So the differentiation of all utility or payoff functions that with respect to each one, so the differentiation with the utility or payoff of ith player with respect to the strategy of the ith player should be 0. So this is to guarantee that we get to the extreme point. Okay. And then the Q is giving only that it can be 1-to-1, so it means that it is for uniqueness, so we have a single solution. And finally, the second derivative should be less than 0, which means that the extreme point is maximum. So because we are looking for the maximum for the utility that every player wants to achieve. So in case that all these 3 achieve it, then we have like a saddle point or Nash equilibrium point. But these conditions are sufficient conditions and not necessarily conditions. Okay. Yeah, so here we have a simple example that we have 2-person game with possible strategies that they are a real number, so it means that they are continuous, And then we have, this is the utility of the first player, this is the utility of the second player, and then we apply the previous condition. So we differentiate with and equal to 0. Then we check that from the above equations that they are unique solution, and we have a stationary point as it is shown here. And actually the second derivative is less than 0, which means that both of them, they are maximum. So they are maximum. So it means that these solutions are saddle point. Okay. This is another example, but here we have three cases and so on. So actually that's all about this part of game theory. So I hope that now it is clear at least what is the game theory, what game theory means, and it is the case that when our intelligent agent needs to take decision, and what kind of decision they should take. They should consider also this utility function or payoff function, and also what kind of strategies that they are available. And finally, they find the saddle point, the equilibrium point, that this one should be played in case of multi-agent environment. So the intelligent agent, if they deviate from playing that equilibrium Nash or equilibrium point, then the other agents or intelligent agents may take like benefit of that, and then they can get provide for them better gain, and for this agent will lose more actually. So in that case, every player should play the Nash equilibrium point in case that it is non-cooperative game. If it is cooperative game, of course we have different conditions, and at that case, in that case we have different conditions. We have different like computation how to find the optimum solution in that case. Okay. So, but remember that in cooperative game, no player is interested to play in cooperative game unless they can get better gain by being in this collaboration. Okay, that's all. So now I hope that we covered this fundamentals part. Remember that is fundamentals. By the way, we have course actually on game theory, a separate course that it is not available every year, but from sometimes that we provide this game theory course with much more details that how to find the solutions in different scenarios. Okay, in these fundamentals now we covered the starting from the in general meaning of intelligent agent. We go through the searching techniques, and after that we provided some concepts of digitization and digitalization and the importance of this in new and in to provide new services. And after that we gave also this machine learning algorithms and the application of machine learning, difference between data and information, how to extract information from data, and the different algorithms of machine learning, and finally the game theory. So what is coming after this fundamental part, it will be some applications. So the next part will be applications, how to apply, for example, Python or some programming language in order to have some like applications of artificial intelligence. Thank you very much, and I wish you all success for the rest of this course. Bye.